Alright, so we are given this distance function, and we want to prove that's a metric, and we want to figure out what the topology resulting from this metric looks like, what the metric space looks like. And one thing that you might notice is that this distance function, we're not restricting ourselves to the real numbers. It's not the real line. It's X is any infinite set, and in fact, you can define this metric for any set. So we've defined a metric here that can be applied to any set, which is pretty general, and so that might make you think like maybe this is a more general thing, and it is. It's a thing that comes up a lot. It's the topology that this metric produces is called the discrete topology. And I'll go into why it's called the discrete topology. But anyways, the first thing that we need to do is prove that it's actually a metric. So to prove that D is a metric, note that if P and Q are elements of X which are not equal, whoa, that was weird. Okay, so if P and Q are elements of X which are not equal, then the distance between P and Q is 1, which is not 0. And the distance between any point P and itself is 0. Okay, and that's the first criteria. You need the distance between any two distinct points to be strictly positive. Or here, yeah, strictly positive, so we'll put 1 is strictly greater than 0. And then the distance between any point in itself has to be exactly, precisely 0. Next, if P is not equal to Q, then the distance between P and Q is 1, because P and Q are not equal. But if P and Q are not equal, then Q and P are not equal, and so the distance between Q and P is also 1. And so that establishes symmetry. The distance between, well, if P and Q are equal, then the symmetry part is obvious. So we don't even need to worry about it. Let's see here. For the triangle inequality, let's see here. For every single, if we just have a P and a Q in X, then the distance between P and itself is 0, and 0 is obviously going to be less than or equal to the distance between P and Q plus the distance between Q and P, because these two distances on the right here are going to be greater than or equal to 0, because we've proven that this distance function is always greater than or equal to 0. Right, so yeah, so the triangle inequality obviously holds when because the triangle inequality usually looks like the distance between P and Q is less than or equal to the distance between P and R plus the distance between R and Q. And here we've just used Q in place of R, and we've used P equal to Q, if that makes sense. So in fact, I'll maybe make that a little more clear when I do the next part. Let's see here. If P and Q and R are in X, and P is not equal to Q, then R can be equal to, at most, 1 of P and Q. And so what this means is that the distance between P and R plus the distance between R and Q, well, if R is equal to at most 1 of P and Q, then the distance between P and R could be 0 if P equals R, and the distance between R and Q could be 0 if R equals Q. So either of these two terms here could be 0, but if one of these is 0, then the other one will not be 0. And so the sum of these two things is going to be at least 1. It could be 2, but it has to be at least 1. And so therefore this is greater than or equal to 1. And so, but 1, because P does not equal Q, 1 is equal to the distance between P and Q. And thus, for all P, Q, and R in X, the distance between P and Q is less than or equal to the distance between P and R plus the distance between R and Q. And that's a triangle inequality. And again here, so what I meant was for the first part, if you actually, in this final form that we see here, if P equals Q, then we know that the distance between P and Q is the distance between P and P, which is 0, which is less than or equal to the sum of these two things, because these two things are obviously going to be positive. So yeah. Hence, D is a metric. Okay, so which subsets are open? So let's take, to determine the open sets, note that for every single P, every point P in X, and every positive real number R strictly greater than 0, be the ball of radius R centered at P. So this is a set of all points whose distance under this metric D, distance from the point P is strictly less than R, is open. If R is less than 1, then what is the set BRP? Well, this is the set of all points, this is all point Q and X such that the distance between P and Q is strictly less than R. That's just by definition. Now, this distance function that we've defined, what are its possible values? The only values it takes on ever are 0 and 1. And since R is strictly less than 1, the only valid value of R, basically, if since R is strictly less than 1, any Q such that the distance between P and Q is strictly less than R must also satisfy the distance between P and Q is strictly less than 1. And so the only remaining option is that the distance between P and Q is equal to 0. So this is a set of all points Q and X such that the distance between P and Q equals 0. But what is this? This is just the set containing the point P, because that's the only point whose distance from P is 0. Every other point has distance 1 from P. And so therefore, this open ball has just one element. Let's see here. So what does this prove? This proves that any set containing just one element is an open set in this discrete topology. And that's why it's called the discrete topology. It's because usually when you think of things being discrete, that means that points are like separated. And here points are sort of separated from each other because every point is itself an open neighborhood. Every set containing just one point is an open neighborhood. But even more is true. So for any subset of X, so A is any subset of X. We have no idea what X looks like, but A can be any subset. A can be written as the union of all points in A of the singleton set containing just the point P. So A can be written in this form. Thus, every subset of X can be written as a union, an arbitrary union, but a union nonetheless, of open sets, and hence every subset of X is open. So this is sort of like, in some sense, the largest topology you can have on a set, because every single subset is an open set. If you have any other topology that, like, if you have any topology, then any set in a topology is a subset of the entire space, and so therefore any topology must have, let's see here, so any set in any topology must be open in the discrete topology, and so the discrete topology in some sense has the most sets of any topology. It's hard to use words like most when you're talking about infinite things because you have to worry about cardinality and stuff. But yeah, this is how can you put the most open sets in a topology. You do that by giving it the discrete topology and just saying, okay, everyone's an open set. So furthermore, if we want to talk about closed sets, if A is a subset of X, then obviously A complement is a subset of X, which means that A complement is open because all subsets are open, which means that A, which is the complement of A complement, is closed. So every subset of X is closed. Alright. So that tells us about the open and closed sets. And now we have to talk about the compact sets. As for compact sets, recall in this particular exercise that X is infinite. Alright, so we have an infinite set X. So suppose A is a subset of X. If A has infinitely many terms, then if we look at the collection here, how should I write this? This is going to be the collection of all... Okay, so here's how I'm going to write it. The collection of sets of the form... The collection of sets, each of these sets consists of just one element, the element P. And so these are all singleton sets. And we take the collection of such singleton sets where each of the singletons are elements in A. This is each of these singleton sets is an open set, and every point in A is covered by one of these singletons because that's how we're defining this collection of sets. And so this is an open cover of A with no finite subcover. And why is there no finite subcover? Because if this collection of sets had a finite subcover, then we would need to remove at least one of these sets. I mean, of course, you'd have to remove infinitely many sets because that's the only way that you would go from infinitely many sets to finitely many sets. But regardless, you would have to throw out at least one of these singleton sets. So you'd have to throw out some set containing the singleton point P. But then if you throw out the set containing just the singleton point P, then there is no other open set in this collection which contains that point P. Because that singleton set containing that point P is, by construction of this collection, the only set which contains that singleton point. So, as soon as you throw out any of these sets, you no longer have a cover of A. As soon as you throw out a set, that leaves one point in A which is not covered by any of the remaining open sets here. So therefore, there is no finite subcover. And thus, A is not compact. If the size of A is finite, say the size of A equals n, and if let's say, let's call this U alpha. I think we usually use alpha when we're indexing arbitrary collections of sets usually. So if U alpha is an open cover of A, then for each P in A, there is some, let's say, here. Let's say that A is, let's label the elements of A. So we know that A has n elements. We'll label them P1 through Pn. Then for each j, we'll say j equals 1 through n, there is some, here I'll call this open cover fancy U. So there is some uj in fancy U such that pj is an element of uj. Thus, we have the collection U1 all the way up through UN is a finite subcover of A. Now this is, just a side note here, this is usually when we say a subcover of something, the A is the thing that's being covered. So it's really subcover is sort of a strange word, because the sub and the cover are referring to different things. So it's sub with respect to the collection of open sets. So it's a sub collection of fancy U, but it's a cover of the set A. So I feel like for this, usually when we talk about these things, it's easy to know what people are referring to. But I feel like to be technical, it might be better to say like a subcover of A with respect to the collection U, or maybe a subcover of fancy U with respect to the set A. I don't know, but typically when you say subcover, you should have two things in mind. You should have the open cover of which you're throwing out some of the sets, and also the underlying set which is being covered. So that's just something to keep in mind, and that's not something that's always clearly stated in these scenarios, but typically you can figure it out by context. So we have a finite subcover of A. Anyways, and so that means that A is compact. Hence, any subset A of X is compact if and only if it is finite. And there you go. This completes the proof. Now, one thing to note here. Heine-Borel doesn't work here. So, closed and bounded are not the same as compact. So, and we see that because every single set here is closed, and the distance between any 2 points is at most 1, and so every set is bounded as well with respect to this metric. So, in fact, every set is closed and bounded, and so it's certainly not true that if X is a finite set, then it sort of works out that sets which are closed and bounded are also compact, because in that scenario, all subsets are compact, and so that's not really super interesting. But it is a little more interesting in the infinite case, where we have an example of a topology in which you have sets which are closed and bounded. In fact, every set is closed and bounded, but only the finite sets are compact. So here's an example of a topology, of a useful and interesting topology, in which it is not true that closed and bounded is equivalent to compact. But yeah, so that just about wraps this up. This is a very important topology. This is definitely something that mathematicians should know about and know the properties of. And yeah, here you go. This is the discrete topology. And of course it's discrete because because things are separated in the sense that singleton sets are open sets. And yeah, there you go.